In this screencast, we're going to talk about integration. As discussed in class, integration is something that we need to do all the time and can often, or in fact even rarely, do analytically. So it's essential to have good numerical routines for doing integrals. Well, as we also discussed in class, there's lots of approaches that can be used for doing integrals, and many of those are implemented for us in Python. So let's dive right in and start using the existing routines. So not surprisingly, in SciPy there are such routines. They're in the module appropriately named integrate. So we can import that, and as usual I like to give it a short name. We can look at the documentation for the module itself. Notice it tells us it does integration and solves ordinary differential equations. That's something we'll talk about in the near future. For integration, it has sets of routines split in the two ways also mentioned in class. If we have a function that we've written down and can define, we can integrate that using various routines. Or if we've evaluated or collected or somehow gotten a table of values that is fixed samples, there's a set of routines that can work on those too without knowing the actual underlying continuous function. We recognize many of the things in here: Trapezoidal Rule, Simpsons Rule, Romberg integration. We talked about those things. Notice that for functions there's also a version of Romberg integration. We have not, and unfortunately will not, talk about Gaussian quadrature. And then it has what's called a general purpose integration or routine called quad, and multiple dimensional versions of that. This is the extremely powerful major workhorse routine that we will use. Okay, so that's nice, that documentation. We should look at that and study it a little more carefully. But let's also look at the routines that are in here, because not all of them were listed in that documentation. In particular, there's Newton-Cotes, which is something we talked about in class, Trap-Z, okay, and various other things. So let's start with Newton-Cotes. So when we first talked about the integration, we talked about, well, one thing that you can do is you can approximate the function using an interpolating polynomial, and that reduces the problem to integrating over polynomials instead of integrating over whatever function you started with. That's nice because we know how to integrate over polynomials, but we've still got to do the integral over polynomials. Well, we did, except this routine does it for us. So this returns the weights and even the error coefficient that we can use for Newton-Cotes integration. It even describes what Newton-Cotes integration is, okay, or at least how we write it. We can rewrite the integral, which is here, as a sum, some step size, which they call delta x, some coefficients, these a sub i's, were the things that came from integrating over polynomials, and then our function evaluated at certain points, and it even talks about and quotes the error term. What we feed to this is the order of interpolation that we want to do. We're going to ignore what this equal is. It doesn't matter for us. What it returns is an array of the coefficients, okay, and the error coefficient. It even warns us, oops, if I don't scroll past it, that normally you only want to use this over a narrow interval, or at least over a region in which the function is not changing very much. If you want to integrate over a bigger region, or a region where some low order polynomial is not a good approximation, then we want to use a composite rule, so which is good practice in general. So let's look at this. So we feed it the order of interpolation. If we do 1, that's linear interpolation. This is what we had called the trapezoidal rule, or at least what we used when we derived the trapezoidal rule. And lo and behold, we see it returns an array of coefficients as the first thing, 1/2, 1/2. What's exactly what we saw when we derived this? We had written it as h over 2. Okay, that's the delta x that was talked about in the documentation. So there is still the delta x, the h, whatever the separation between the 2 points is out, that we have to take into account. But other than that, the weighting between the evaluation of the function at the 2 endpoints is just 1/2 for each of them. It even gives us the coefficient for the error term, which again we had quoted as -1/12. So great. We can do this for quadratic interpolation. This we had called Simpsons Rule. Notice that this gives us the coefficients 1/3, 4/3, 1/3. Again, exactly what we had written down. It even gives us the error the coefficient for the error term. We can now go crazy and start doing this for higher and higher order interpolations. So third order, fourth order. Okay. If we wanted to do that, these are the coefficients that we would use. We can even go crazy and do this for a very high order. It will happily return the coefficients for us, though it doesn't make much sense to actually do this. If you notice these coefficients, the largest ones are of order 10 to the 8, the smallest ones of order 10 to the -1. That's about a 9 orders of magnitude difference between these two. Numerically, what that means for us is that we're going to run into precision issues. Okay, when we have such large orders of magnitude differences between coefficients, that's when we start running into problems where this becomes numerically inaccurate. But if we wanted to do it, or we want to know the coefficients for some crazy order interpolation, it will happily give them to us. Now we could use this to build our own routines for doing things like Trapezoidal Rule, Simpsons Rule, or these higher order ones. Fortunately, things like Trapezoid and Simpsons Rule are already implemented for us. If we did want to do higher order interpolations, we would have to write our own routines for doing that. So for the Trapezoidal Rule, there's a routine, trap-z. Okay. Notice that it does the Composite Trapezoidal Rule. Okay, because we pretty much never want to use just the Trapezoidal Rule. If we did, this routine would do that too. Okay, because what this takes in, we feed it y. Y is an array that has the, well, calls it the input array to integrate. What's contained in here are the values of the function that we want to integrate, evaluated at certain points. We can specify those certain points as either by feeding it x. X is also an array. Okay. This is useful if we have points that are not equally spaced. This tells the routine exactly where those points are. On the other hand, if they are equally spaced, we don't have to pass in x. We can just pass in what the delta x is, what we had called h when we derived this in class. Okay. And so we can just tell it, you know, if it's 0.5, 0.1, whatever, feed in that value here. This also has an option called axis, which is not something we're going to talk about very much. If y doesn't have to be a one-dimensional array, it can be a multiple-dimensional array, and this would then tell it which dimension to use for the integral. So you could only integrate, or you would only have to integrate part of it. What it returns is the value of the integral that we've gotten from the Trapezoidal Rule. Okay. It gives a handful of examples here, okay, which you should look at and feel free to run yourself. Okay. For our purposes, though, let's just pick a simple function for which we know the answer. So let's do the integral of the sine, okay, which we know is just minus the cosine. Let's start by picking some values. Let's integrate from 0 to pi over 2. Let's start with just 5 points. Okay. Again, what y is supposed to be is it's supposed to be the function evaluated at these points, so we can get that. So for fun, let's just look at this, plot x and y. Let's plot it, I don't know, as red circles and connect them by a line. And let's make sure the plot shows up. Okay. So we've evaluated the function at these particular points, and we want to estimate the integral. How does the Trapezoidal Rule do that? Well, it does that by doing linear interpolation, i.e. draws these straight lines between these, and then calculates the area of this region, the area of this region, etc., and adds them all up. And so we can do that. Okay. And now we can specify the x values either as just the array that we constructed, x, okay, and that returns the answer, or since we used equally spaced points, we can put in the equally spaced points, or the separation between the equally spaced points, which is just the difference between any two of them, okay, and that gives us the same answer as it must. Now, again, in this case, the routine itself doesn't tell us or give us any indication as to how accurately this has gotten the answer. Okay, we don't know. In this case, we know what the answer is. We know that if we integrate the sine, we get minus cosine. If we do it from 0 to pi over 2, we're going to get 1. So we know that the answer is supposed to be 1 and that this is reasonably close. Okay? But if we didn't know that, okay, or that is, if we don't know what the true value is, then a useful thing to do is to do the integral, but now with more points. Let's do 10 points. Okay, we need to reevaluate our function y is equal to f of x. And we can now rerun this, and we see that yes, it does, the answer does change, and in fact it changes noticeably. It changes in the second digit. Okay, so we haven't converged on a good answer yet, again depending on how accurately we want this. Okay. We do see, again, knowing the correct answer is supposed to be 1, that it is getting closer to the correct answer. And so we could continue adding points until we were confident or comfortable that this is converging on a good answer, at least to how many ever digits of accuracy we decide we need. Okay. So that's the trapezoidal rule. We can, of course, instead use Simpsons Rule, and that's implemented for us as simps. So again, it does this using Composite Simpson Rule. The structure of this is exactly the same, except for this extra thing, but notice y, x, dx, axis, all of these are the same. It has this extra thing because remember Simpson's Rule is using quadratic interpolation, and we need 3 points to do quadratic interpolation. And so what do we do when we don't have a multiple of 3? And so that's what this even thing is about. There's different choices we can make. Again, we're not going to make a big deal out of that right now. And in the notes, it even talks about this a little bit more. So anyway, an extra thing we need to worry about. For our purposes, though, we can just use it the same way. And again, since it's called the same way, it's easy to change trap z into simps, get a new answer. Notice that the answer now is more accurate using the exact same data, okay, the exact same y, the exact same separation, of points. Comparing the trapezoid rule to the Simpson rule, we get a much more accurate result. Okay, now an extra digit of accuracy, really. Again, that's to be expected, or at least hoped for, because that's what Simpson's rule does. It uses more points for the interpolation. It hopefully does a better job. It should have a smaller error term, and that's exhibited here. Okay, so once again, we could continue on doing this with more points and whatnot to be sure that it's converging. Of course, there's other routines. There's the Romberg integration, and so here it talks about the Romberg integration, okay, using samples of some function. Now the calling's a little different. We feed it y and dx. Now the points have to be equally spaced. Okay, we don't have the option like we did in the composite trapezoid and Simpson's rules. Furthermore, y has to be a vector with 2 to the k plus 1 equally spaced samples. Okay, and it's important that we have this exact number because of how Romberg integration works. Okay. We have the axis thing again, which we're not going to worry about, and show, which will give us more details. Okay, so we'll look at that in a second. So what that means is we should regenerate this, okay, and do 2 to some k. Let's choose 5. So 2 to the 5 plus 1 points. Okay, so those are my new x values. So a lot more points. We can evaluate y at that. And now we can apply Romberg integration to this. So y and dx, again, we have to feed in the separation. Okay. And there we go. Okay. It gives us an answer. And notice that, again, knowing the correct answer, it gives us incredibly close to 1. Okay, so this has done an incredibly good job of getting us the correct answer. This is doing Richardson extrapolation. So when we played with that before when talking about derivatives, we saw that, well, what it's really doing is it's building this big table of values, and we can see that table by using show equals true. And so here it is. And so we can even see how quickly it's converging, because if we look at these values along the diagonal, just as we did before, we can see that, or see how it's improving as we go along. Okay. Now, it doesn't print out all the digits, so it looks incredibly good. We're getting exactly 1, but that's not true. This value is not exactly 1. It's this, 0.999, so there's lots of 9s in there. But anyway, this then shows us what we're used to seeing from Richardson extrapolation, and at least from the table that we can construct from it. Okay, there's one other routine, this cumulative trapezoidal, I guess it's really the cumulative integral using the composite trapezoidal rule. There we go. What this means in short is it's using the trapezoidal rule, but when we did this before, it returned a single number. So it did the integral over the full region. What this does is this does the integral along each step. So it does the cumulative integral. In other words, this does the integral from the starting point to the next point, to the second point, from the starting point to the third point, from the starting point to the fourth point, all the way up to the end. Okay. So it returns an array. Okay, again, there's various examples here. Maybe it's best to just run it. And its structure is very much the same as what we've seen before. So hopefully this will work. And so again, this is doing an integral from the starting point to the first point, second, third, etc. I'm using the y and x that we used for Romberg, so there's an awful lot of points in here. Okay. So what this should be doing is this should really be returning the cosine function, okay, evaluated at all these intermediate points, the final one being the total integral over the whole region. Okay. There are occasions when this is useful, in fact when this is exactly what we want, and so this is just a convenient routine for, that does that for us. Okay, so that was all the functions that operate on tabulated data. What we're often interested in, though, is functions that, or things that operate on a function. And so for Romberg integration, we can there's the routine Romberg, okay, which does that for us. So if we look at it, the structure of this looks very similar to what we saw, for example, with root findings routines. You feed it a function, you feed it an interval, and you can pass optional arguments to our function. There's various tolerances, okay, that are similar. We can get more information by using, in this case, show. We can determine the number of steps of Richardson extrapolation it does. That's what divmax does. And then this is an optimization thing. Okay, is the function that we are going to evaluate, can we feed it an array? In other words, is it a vectorized function? If it is, then it's advantageous to set this to true, because then the algorithm, or then it can run much faster, because it can just call our function once to evaluate everything that it needs, instead of having to do it in a loop. So for the most part, these are the first four things are the things that we're most interested in. Vecfunc is useful, and show can be useful. Okay. Again, it describes all of these, which I just said. You should read them at your leisure, and it gives some nice example of showing how this is done. So let's just do this. We wanted to do the integral of our function, which we're calling f, which is just the sine, from 0 to pi over 2. Okay. It is a vector function, but we don't have to tell it that. And lo and behold, there it goes. It gives us an answer extremely close to 1. We can do show equals true, and it shows us the table that it constructed. It even tells us how many function evaluations were required, in this case 17. Okay. and the final value that it ends up getting. Okay, so again, it's a lot like ROM, except it does, if we have the function, it can do the evaluation at the points that it needs instead of us having to do it for them. Okay. The super powerful routine is called quad. Quad can do pretty much everything, and just its power also comes with a lot of complexity, at least if we want to use all the features. So again, we can start with just the main things. Okay? We feed it a function, we feed it the range over which we want to integrate, and we can pass optional arguments to our function. With that alone, we can make tremendous progress. Then there's various tolerances, we can get full output, and then a whole bunch of other things which we're not going to say very much about at all. Okay? So again, computes a definite integral, can integrate a function from a to b, possibly over an infinite interval. That's something we'll talk about in class using technique from this particular thing. And in fact, this is so powerful and so, well, at least can be complicated, that it has its own function called quad explain, where you can get more information about some of the more, well, as they say, esoteric, but more complicated things that it can do. Okay, so we'll look at that briefly. But for us, really, what they say here is what we need. Okay, these are the most important parameters for us. Okay, this is the most important things that it returns. It returns a number, and it returns an estimate of the error, which is very important and useful. And then it can return extra things. If we ask for full output, it will return this extra information. Okay? And then it does talk about some other parameters, other things we can look at, and it gives us some examples of how we would use it. Okay, whoops. Just for fun, we can run this function and it prints out a whole bunch of information. Yes, a whole bunch of information about all the various things. The first part here is a little useful because it does tell us about what gets returned. This info dict thing, if we ask for the full output, so things like the number of function evaluations, and then some other details which we probably won't care too much about, and then various other sophisticated things it can do, and special types of integrals that it can handle. If we have something multiplied by a sine or cosine or various other functions, it can use more sophisticated routines for that and return various other pieces of information. It even tells us something about the methods that it uses, Clenshaw-Curtis method, Chebyshev moments. Again, these are details which are nice and we could learn more about but don't really need to know. Okay, so let's just go ahead and use it. Okay, so we want to integrate our function from 0 to pi over 2. Okay, there we go. It returns pretty much 1, and it gives us an error estimate of 10 to the minus 14. Okay. Now, it's great that it does that, and we should always pay attention to that to see whether we believe what this is doing or not. But we're often really just interested in the value. So the fact that it returns 2 things is slightly annoying. So there's a few things that we can do about that. We can store this in something. Okay, we can store this. Remember, this is called a tuple, so it's a read-only list. And then res 0, or the first argument, the first entry in this list, is the value that we want. As shorthand, remember this is returning a list, so we could just take only the first entry if that's all we're interested in. Again, it's a little dangerous to do this, or at least we should always have looked at the error beforehand to be somewhat confident that it's working. But if we go ahead and just keep the first entry, that will give us the integrated value. So again, that's just some shorthand that we can use. We can also, as it said, get the full output, in which case it returns all this other stuff. Okay. It returns what's called a dictionary, so that's the thing in these squiggly brackets. Okay, it has a key and then various data stored in it. So that's nice. So let's I don't know, call this result, error, and info. Okay, it returns these three things. Result was that number, error was the error estimate, and info was all this other stuff. Okay. Again, perhaps the most important thing in here for us is the neval. Neval tells us the number of function evaluations that it did. So we can get that, whoops, okay, by accessing the dictionary. Okay. Now it has a key, which is a string, so we can pass that in by name, in quotes, doesn't matter whether it's single or double quotes, and that returns the number of function evaluations that it did. Okay, so despite showing up last and spending more time on all the other things, quad is the truly powerful routine that we're going to use the most. Okay, because it has built in all the things that we talked about. Okay, the adaptive quadrature. It decides how to split up intervals and does all that work for us, and can even do some more sophisticated things, as we will discuss in class. Okay? So you should at this point now be able to integrate pretty much any function, and we will play with some of those examples in the near future, in the lab, etc. Okay.